For any calorimetry problem, the most important thing to remember is whatever heat is like gained or lost by your calorimeter is going to be equal in magnitude and opposite in sign, so just times by -1 of the heat released or absorbed by the thing you're interested in. Let's just call it Q for the reaction, or it could be a process. Like in this case, it's a hot bit of glass cooling down. So that's what I define as the reaction, okay? So in this case, my Q for my water, which is part of the calorimeter, is going to be equal in magnitude, opposite in sign to Q for my glass. And how these questions usually shake out is that you have all the information you need about the water or about the calorimeter, so you can calculate Q, and then therefore, Q for the thing you're actually interested in. And if you have Q and you'll have like delta T or something, you can rearrange for the heat capacity. If you have the heat capacity and you've just calculated Q, you can solve for the change in temperature or back calculate the initial temperature. Another important thing to remember about these kind of problems is the definition of thermal equilibrium. That being that if you have a hot object and a cold object, they come together when the excess heat from the hot object flows across a temperature gradient to the cooler object. At some point, that dynamic process is going to mean that your final temperature of both the initially hot and initially cold object is going to be the same. It'll be somewhere in between the two temperatures, depending on the starting temperature of each of them and the heat capacity of each of the individual objects, okay? All right, so enough jibber jabber from me, onwards to actually trying to solve this thing. So we're going to want to use our expression between heat capacity and heat for water, and we've been given the mass of water, so I'm going to use the mass times the specific heat capacity, and I'm going to be really specific, the mass of water times the specific heat capacity of water times delta T for water. Okay, so that's going to be the final temperature minus the initial temperature of water. Okay, because notice the water and the glass start off at different temperatures, so you have to read the question really carefully. So the mass of the water is 250 grams. Specific heat capacity of water you're not given, but that's okay because that's a constant you can just look up. In fact, it'll be in your ALEKS like table of constants, but I know it's 4.186 joules per gram per Kelvin. And then my delta T is my final temperature of the water minus the initial, so 23.9 minus, temperature starts off at 21. So notice the initial temperature is warmer, sorry, the final temperature is warmer than the initial temperature because the hot glass has caused the water of the calorimeter to heat up. So delta T should be positive. So Q for the water is going to be a positive number. Makes sense because that means the water has absorbed heat. Where's it absorbed it from? It's absorbed it from the glass. So Q for the glass is going to be the same numerical value of Q, but with a negative sign. So without any further ado, let's see if I can use a calculator. Debatable. 250 times 4.186 times 23.9 minus 21, so that's going to be 2.9. I'm not even going to mess around with parentheses today because my calculator just hates me. 3034.85, and that is, of course, in joules, okay? The grams and the kelvins all are going to cancel out. All right, so then Q for my glass is going to be equal in magnitude, opposite in sign, so minus 3034.85 joules. Okay, so what do I want to know? I want to know the specific heat capacity of the glass. Okay, so I'm going to rearrange Q equals M CS delta T. Okay, so that CS is my subject, the specific heat capacity. So then that's going to be Q over M times delta T. And remember, that is delta T for the glass, okay? So just be a little bit careful with that, okay? And again, the signs are going to sort themselves out, okay? So I've got a minus sign for Q, 3034.85 joules. My mass of my glass was 59.5 grams. And my final temperature is 23.9, same as the final temperature of the water. It has to be, otherwise they wouldn't be at thermal equilibrium. But the initial temperature was 97.3. So notice that's going to come out to be a negative number. 23.9 minus 97.3 is minus 73.4. Okay, so a minus divided by a minus is going to give me a plus. So I get a positive number for the specific heat capacity, which I should do because There's no such thing as a negative specific heat capacity. So 73.4, see if I can remember that. 3034.85 divided by, I'll do the 73.4 first before I forget what it was, times 59.5, close brackets, equals 0.6949, blah, 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 blah. Two significant digits, right? So that's going to be joules per gram per Kelvin. So there's my specific heat capacity. And notice it comes out positive because the minus and the minus are going to cancel. It's a beautiful thing.